Alright everyone, what I'm going to do now is go over problem number 2 from the old exam problems. Essentially, this problem, initially it asked to solve for the centroids x bar and y bar for the shape shown below. What I'm going to do is I'm going to solve for both of those things, but then I'm going to add a second part to this problem, which is to solve for the moment of inertia about the centroidal y-axis. And I'll go over how to do that in a little bit after I go over this first part. So the first thing that we need to do to solve for x bar and y bar is let's just make sure we're all on the same page and write down the equation for x bar, which we know is the sum of the area of every shape times the location of the centroid of that shape divided by the sum of AI. And we know that y bar is equal to the sum of AI yi over the sum of AI. So the thing that I like to do in these types of problems is set up a table. And setting up a table will help you organize your work and make it far more easy to do the math, to keep track of everything, and solve the problem. So what I'm going to do is I'm going to set up that table and have it appear magically right here, and then we'll get started solving the rest of the problem. Alright, so what I've done is I've set up a table, and the first column in our table is shape. So the first step in all of these problems, maybe after you've written your table, is to figure out how many shapes you have. So you should always be trying to identify as few number of shape as you possibly can for these types of problems. So the shapes that I identified were the triangle over here, which we can see. I can see also that we have a rectangle here, had we taken out this quarter circle. So shape number 2 I've identified as this rectangle, and shape number 3 is this quarter circle. Now, what I would say is, in theory, you could have done this problem and you could have said, hey, I have one giant rectangle right here, and then I have a hollow triangle and a hollow quarter circle. That would be totally acceptable to do the problem that way, because again, you would have only 3 shapes. So I highly recommend you try and find 3 shapes in the problem, and if you find any more than that, you probably have made it far too complicated, or more complicated than it was necessary. So shape number 1 is our triangle, shape number 2 is our rectangle, and shape number 3 is our quarter circle. Okay, now we just have to solve for the area of everything. Well, the area of our triangle is 1/2 the base times the height, which is 1/2, 150 times 300. The answer to that is 22,500. I'm going to go through and solve for the other areas because we'll save us a little bit of time. Okay, so I solved for the area of the rectangle. That was its base 200 times its height 300, gets us 60,000. And the area of our quarter circle, as is identified up here, is pi over 4 r squared, basically 1/4 of the area of a circle, which should make sense. We plug that in down here, we get 17,671.45. Now something I want to point out that's actually fairly important in these types of problems is that I've made this negative. And the reason I've made this area negative is because this isn't actually a part of the shape. It's a piece that's been omitted from the overall shape. So the area should be negative. So when I add up the areas in my total row, I'll get that the total in this column is 64,828.55 millimeters to the 4th. Sorry, millimeters squared. Now what I have to do is I have to solve for xi. So to solve for xi, I'm going to be using this point right here as our datum, because you can see our y-axis goes through the shape and our x-axis is down here. Now, in theory, you can choose any datum point you want. You could have chose down here, you could have chosen up here in theory, but usually you want to choose the intersection of the xy axis, because most exam questions will ask you to solve for the centroid location from each of the axes. So, for the xi, we know that the centroid of a triangle is about right here. That's going to be 1/3 the distance from the bottom side, which is going to be negative 50 millimeters. Again, because this point is 0, 0, I have to go 50 millimeters to the left, or be in the negative territory, to be able to do that. So now I can multiply these two things together, AI, XI, and I get that the answer here is negative 1,125,000. When I identify the xi of the rectangle, well, its base is 200. I know that the centroid of our rectangle is about right there, halfway over, so it's 200 over 2, which is 100 millimeters. Now, for our quarter circle, what we can see is we're given x bar, but x bar is from the flat edge. So what we've been given for our quarter circle is essentially this distance here. But really what we want is we want this distance from the datum point to the location. So to be able to get this distance x, we'll call it xi, I guess. Xi is going to be equal to 200 minus 4 times 150 over 3 pi. And when we do that math, we get that this is 136.33. Now we can multiply ai by xi for both of these things right here. So for our rectangle, we get ai xi is 6 million. And for our quarter circle, we get ai xi, because of our negative over here, we get negative 2,409,148.78. Now we can total this column right here, and we get 2,465,851.2. Now we plug those things up here. So we plug in our 2,465,851.2 divided by our total area, which was 64,828.55, and we get that our x bar is equal to 38.04 millimeters. There we go. Now we'll do the same process for y bar. So now we just have to look at what's the yi of each shape. So our triangle, its height is right here. So our yi is this distance right there. That's 1/3 the distance from the bottom. So if the height's 300, then we have that this is going to be 300 over 3. This is equal to 100 millimeters. For our rectangle, it's 300 meters tall. So it's going to be 300 over 2 equals 150 millimeters. And last but not least, for our quarter circle, our y bar is just 4r over 3 pi, which in this case, when we're going from the flat to the location in that direction, we're actually good. We don't need to do anything special. So this is just 4r over 3 pi, which is going to be equal to 63.6. Now what we do is we multiply our area by the yi in each column again. So over here we get 2.25 million. Here we get 9 million for our rectangle. And down here we get negative 1,123,904.2. We add everything up and we get 10,126,095.78. So now we just take these numbers up here, we plug them in, and we get our answer. So we have 10,126 and 95.78 over 64,828.55. This will give us a y bar of 156.2 millimeters. So box my answer, put all that right there. And what you should always do in these problems is make sure you check your answer and that it actually makes sense. So we get x bar is 38.04. So that basically tells us that our x bar of our whole shape is about here. That is x bar of our whole shape. Now that makes sense because it seems to be about in the middle. Now if we look at our y bar is 156.2. So that tells us that y bar is a little bit up here. And that tends to make sense as well because down here we're losing this area. So our area almost should be more, our y bar should be closer to the top of our shape. Something I see students do a lot is they'll get an answer that says y bar is 500 millimeters. If that were the case, that would tell you that y bar was like up here. What are you doing? You can't have the y bar or the x bar of the shape be outside of the footprint of the shape. So you have to know that the centroid must always fall within the footprint of the shape. So I've checked our answers, at least conceptually, and it makes sense. Now what we'll do is I'll pause the video and we'll move to the second part, which is going to be this additional part to the problem I've added, which is how to solve for the moment of inertia of the shape. All right, now what we're going to do is we're going to solve this bonus question, which is to solve for the moment of inertia about the centroidal y-axis, i.e. IYC. So first question is, what is the centroidal y-axis? Well, in our last part of the problem, we solved for x bar and y bar. And we solved that x bar was equal to 38.04 millimeters. Well, what that means is that to find the centroid of our shape along the x-axis, we had to travel 38.04 millimeters to the right. That gives us this line right here. So here's our x bar, here's our line, and what this is this is the y centroidal axis. So this will be the point that we're summing our moments of inertia about. What we know is that for any system, that the moment of inertia of the system is equal to the sum of the moment of inertias of every single shape. And we know that the I of every shape, the moment of inertia of each shape, is equal to the moment of inertia of that shape about its centroidal axis, plus any adjustment factor to account for the fact it may be rotating away from that point. Okay, so what we're going to be doing is we're going to be doing the I of each shape. So we need to basically figure out the I of each shape about its own centroid plus AI di squared. So what I like to do is I also like to create a table for this system as well. Now you don't have to do this, but I like to think it keeps things organized. So what we'll do is I'll plug in our first column, which is the IC. Now, essentially what we'll be doing is we'll be finding the moment of inertia of each shape about its own centroidal y-axis, and then adding in this adjustment factor over here. So let's just write that down. So this is the moment of inertia about the centroidal axis. And this is what I like to call the adjustment factor. And this right here is known as the parallel axis theorem. All right, so let's get back to work. IC for a triangle is, if you look at your table that will provide you, is going to be equal to 1/36 height times base cubed. You'll also sometimes see a different equation, which is that it's base times height cubed. Now, for our triangle, we're rotating about this axis here, the triangle centroidal axis. So if the triangle got wider, it would be much harder to rotate about that axis. If the triangle got taller, that wouldn't really matter as much. That's why base cubed, as the base gets larger, the moment of inertia or the resistance to rotating goes up. So that should make some sense. Think about a figure skater as they spin. If a figure skater was trying to spin through this axis right here, I'll even draw this little picture of our figure skater. If our figure skater was trying to swing about this axis right here, as their arms got wider and wider and wider, they would spin slower and slower and slower. So the distance that matters is always the distance that's perpendicular to the axis of the rotation that you're doing. That's a way you can check to make sure that the numbers you're plugging in actually make sense. So this is going to get us, for this particular problem, 1/36 times the height, which is 300 for our triangle, times the base cubed, which is 150. This gets us a moment of inertia of a whopping 28,150,000 125,000. So that took up a lot of space, but that's all right. We don't have that much more stuff to do. Now for our rectangle. We know that for a rectangle, it's going to be 1/12 base height cubed, or 1/12 height base cubed. In this particular case, because we're rotating about this axis right here, the distance that we care about is the 200. So it's the base. So what we're going to get is 1/12 height times base cubed. This leads us to the fact that we've got 1/12 times 300 times our base, which is 200 cubed. And this gets us a value of, holy shnikes, 200 million. Now what we have to do is our quarter circle. Now this isn't found in your table, but we can see up here we've got two options. We've got Ix and Iy is 1/16 pi to the fourth, or we've got Ixc and Iyc equals this funky looking thing right here. Well, I can tell you right now that you almost never need these on the exam. The reason is because that's telling you the moment of inertia from this axis. But we don't care about that axis. We want the I-centroidal for each shape. That's exactly what we have in our parallel axis theorem equation. So what we want is we want this. And we can see that these are both the same. So for our particular case, what we're going to do is take in our Ixc, which is the same as Iyc, which is 1/16 pi r to the fourth, which is 150 to the fourth, minus 4r to the fourth over 9 pi. When we do this, what we get is that our answer is equal to 27,781,830.6. Now another key here is because this is a hollow area, we have to put a negative sign, because this is actually not really part of the shape. So to rotate this whole shape, it's going to be easier because this piece has been taken out. We have less mass in our system. Now what we'll do is we'll sum this column over here, IC, and we get 200,343,169.4. Okay, now what we need to do is, from before, we had written this column, XI. So I'll just bring that back here. We had negative 50 millimeters, 100 millimeters, and 136.33 millimeters. What we're now going to do is I'm now going to compute DI. DI is going to be the absolute value of X bar minus XI. So in this particular case, what we get is the X bar is the X bar of our shape. So for this particular case, we have 38.04 from before, minus the XI. Well, what was the XI over here? Well, it was negative 50. So we have 38.04 minus negative 50. So this actually gets us a value here that the DI is 88.04 millimeters. Well, what is this DI referring to? Well, essentially, if this is the X bar of the shape, then the DI for our our triangle is the distance from here, which is 38.04 plus another 50. That's where this comes from right here. We had to go to the left, 38.04, and then to the left, 50 more. So the distance between this axis here and our centroidal axis is 88.04. And I'll put that there. We now repeat that process for the rest of our shapes. And we say that DI here is 38.04 minus XI, which is 100. So if we look, what we're essentially doing here is that the distance from here to here is this distance. This is our di for the rectangle. So the distance between those two things right there is 61.96. And last but not least, down here we have 38.04 minus 136.33. And down here we get the answer is negative 98.29. Now if you forgot to do absolute value and had these as negative, that would be fine because the di is actually squared in our term anyway, so it won't make a mathematical difference. Now we're pretty much done. There's one last thing we need to do, which is to multiply the area times di squared. So now we have ai di squared. We have the areas from the previous part of the problem. The area of our triangle was 22,500 times di, which is 88.04 squared. This gets us a value of 174,398,436. Over here for ai di squared, the area of our rectangle was 60,000. So we get 60,000 times 61.96 squared. And last but not least, down here we have the area of our quarter circle, which was negative 17,671.45 times 98.29 squared. So now we've got everything in this column, so we can add everything up. And I'll just plug in these numbers right here. So for a rectangle, we'd have got 230,342,496. And down here, we would have gotten negative 170,722,537. So the total in this column is 234,018,395. So, again, notice here that our moment of inertia adjustment factor is also negative. So these two terms are subtracting in the summation of all of these things. So now pretty much all I have to do is I just add this number and this number together, and I get the total moment of inertia about the centroidal y-axis of our shape, which is going to be equal to 434,361,564.4 millimeters to the fourth. And it's important that you include that unit there. Now, I find that the table is very helpful because if you combine your table from the previous part, you can keep your AI, your XI, and you would just be adding a few more columns to the right. Because usually on the exam, you won't be asked for both X bar and Y bar, you'll be asked for one or the other. So we would cancel out these two columns here. You would add in essentially this column and these two columns right here, and you would be able to get your answer much more easily and much more efficiently and neatly, which we always like when we're grading the exam. So that's it. That's how you approach a typical centroid problem. You solve for the centroid, and then you take the moment of inertia, usually about that centroidal axis. And that's it. Good luck on the exam.